Welcome to lecture 28. Today I am going to speak about the construction of oxygen lamps. The main things which involves are this particular oxygen lamps is made up of three concentric steel tubes with having circulation of water continuously. And one more thing you need to notice that the tip of this steel tube, this tip is made up of copper, which is surrounded by steel. By welding it is being constructed. Why? Because this particular oxygen lance is exposing to very high temperature, and because of the heat transfer and thermal conductivity to be balanced, we use for more heat transfer we use copper tip on this. And one need to notice that if this particular nozzle is single nozzle, assume that the flow of oxygen is coming from this direction, and this is a typical nozzle design. This is axis of oxygen coming from the top of LD converter. So I can call it as a radial velocity, this particular surrounding, and whereas along with this axis is called as a axial velocity. And this particular oxygen gas may entrain or may interact with surrounding gas, such as all those particular things dissolved in oxygen lamps are, let me repeat, this incoming oxygen, flow of oxygen, axis, along the axis it is called axial velocity. There is one more assumption. If you think realistic simulations, it also interact with the surroundings of molten steel, and there was few terminologies which were used in this oxygen lamps and molten metal interaction. This particular, from this tip to surface of the molten steel, it is divided. The first part is called as a potential core of oxygen lamps, and from this particular oxygen lamps tip to next stage is called supersonic core, supersonic velocity, potential velocity. So based on that, these things are, the distances are categorized, which are called radial and axial velocities, and there are dependency. Radial velocity keep decreases, and axial velocity, as the time proceeds, it decreases. Coming to the, what is the spread of this oxygen jet? How do we understand? So what will be the spread inside the molten metal? Even you are maintaining the distance from surface of the molten steel. So how do you understand? There are simple formulas analyzed. You can understand, you can get an idea. The medium of surrounding to the oxygen jet, in this case it is a molten steel, and constantly changes from the starting point to ending point as the time proceeds because of the surrounding interaction. So it is decided that it is the spread of jet is can be estimated by the density of surroundings, solid wall, and density of jet, gas jet. If that particular ratio, surrounding density, molten steel density, and this particular jet density is less than 1, it is understood that it is being assessed as a spread is low. It means the length of the supersonic and potential core is longer, and if it is greater than 1, spreading is high, the length of supersonic and potential core will be smaller, it will be compressed. In this case it is nothing but tensile. So you can remember with these things. Here I am going to tell you about the interaction of oxygen jet with hot metal So how does it interacts? How do you assess? How do you calculate the incoming oxygen from the oxygen lens tip to the surface of the molten steel? It can be characterized by a parameter called Jetbot Interaction, which is expressed in terms of jet force number. It is a ratio of gas pressure and nozzle diameter, oxygen lens diameter, and lens height from the molten steel to oxygen tip lens height. It can be characterized. Remember these problems, there will be numerical problems. So in the final exams and the gate examinations. And the jet velocity can also be calculated by the other parameter such as Mach number, velocity of the incoming oxygen gas, and velocity of the sound it creates inside the molten steel. So how do you calculate the sound of the velocity? For example, the sound in steel is a standard value around 4500 to 5500 meter per second. But within the steel, molten steel, in this particular situation, how do you calculate? It depends upon chi and universal gas constant, the temperature at that particular location. The chi is calculated as the constant pressure and constant volume ratios, which is isotropic constant with respect to those gases, and universal gas constant, the standard value. Temperature supposed to be taken in a Kelvin. You can calculate. But there is another dependency. You can characterize this Mach number. If it is equal, you can say that it is equal to the sound velocity of the liquid steel. If it is less than 1, the exit from the nozzle, the oxygen exit and it interact with the molten bath, that is the velocity of nozzle is smaller than the velocity of the sound and standard, the sound velocity, and in the steel. And if it is greater than 1, the velocity is greater, velocity of oxygen rate is greater than the velocity of the sound. And design of this single nozzles will depends upon this parameter. The supersonic jet should penetrate the bath adequately or optimize. It should not be very high speed. It should not hit the wall of the molten metal converter, and area of the impact should be maximum in a radial direction and axial direction, so that you will be getting the optimum results, optimum stirring and homogenization of the steel quality. And there are two types of nozzles are in practice in the industries. One is the convergent nozzle, the other thing is designed converge and divergent nozzles are in practice. In this situation, it is approximately less than or equal to 1, the Mach number. It is greater than 1. So depending upon the requirement, if the quality of the steel is more heterogeneous, before refining and purifying, converting the iron into the steel, you use convergent divergent type nozzles. And multi nozzles, instead of single nozzle, if there are multiple nozzles, how do you characterize the spreading of oxygen jet inside the molten steel? The axial velocity will be the maximum, or jet radius, one particular jet radius is maximum along the axial direction, and along the radial direction, along this particular radial direction, for example, in one situation after 5.7 meter per second, the radial position is increased. The radial position will be longer, and after the maximum velocity is achieved, it slowly decreases. And this is the practical view of oxygen lens and LD converter as a reference as shown at the left side. And coming to the area of impact of oxygen jet on this particular molten steel bath can be increased by changing the single nozzle to multiple nozzles. How does it occur? It's basically the angle of from the axis to this particular nozzle, axis line to nozzle, the velocity. For example, in this situation, if the angle is lower and that particular jet subjectance is coalescence, or you call it as a interaction of jet with the molten metal surface, is at this distance. If it is increased higher angle such as 15 to 16 degrees, nozzle number of nozzles are 5, it coalesces at larger distance. These schematics are witness for those things. Now these are the practical schematic of oxygen, multiple oxygen lance jet. In the case of multiple hole nozzle, so how do you calculate the number of nozzles? If I give you LD converter steel capacity, if I give you the diameter of single nozzle, how do you calculate number of nozzle? Using this simple formula, molten metal in capacity of tons and nozzle diameter. So only unknown parameter is n. This is into 7.43 into 10 to the power of minus 3. You can calculate. For example, this situation, the n is, if you substitute all these things here, n will be coming 4. This particular number of nozzles there are 4, it suggests. And how do you calculate the performance of oxygen lance? It can be decided by the following few parameters. Try to understand. M star is momentum flow rate of the oxygen jet in bath, and density of liquid steel, and acceleration due to gravity, and height of the lance above the molten metal bath surface. N are number of nozzle, and D n star is the diameter of the nozzle, and P naught is applied pressure in bar. All the units also mentioned here, and P is atmosphere pressure, small p, and P naught, and MT is capacity of molten steel in tons, how much it could produce. Pi is dimensionless momentum flow rate when you calculate M star by rho L and gravity due to acceleration due to gravity, and X the height of the lance above the bath. So you will be getting the dimensionless value. And let me take one of the example with those formulas. If I give you the molten metal capacity produced by LD converter, and nozzle diameter used for this process is 0.035 meter, and the lance height above the molten metal surface is 3 meter, and the liquid density, the density of molten steel is 7000 kg per meter cube. Calculate this following parameters. How many number of nozzles are there? So as a previous problem you can calculate. And what is the applied pressure? So based on the atmosphere pressure you can calculate atmosphere pressure. There are formulas in the previous slide. Momentum flow rate and dimensionless flow rate can be calculated. Depth of penetration inside the molten bath, which is H, can be calculated. For example, in few examples, if depth of penetration H is 0.23 values, 0.23 meter, and lance height is 3 meter X value, and dimensionless flow rate value, momentum flow rate value is 0.00219, then the characteristic behavior of oxygen jet is assumed as the shallow penetration. The other situation, it is called deep penetration. So please try to notice all these particular parameters and try to characterize these oxygen jet values.